Our next speaker is Professor Wehenkel from the University of Liège. So, Luis, whenever you are ready, it's all yours.
First of all, I would like to say thank you to the organizers of this very interesting workshop for inviting me to give a talk. I think my subject is a bit, let's say, I would not say completely out of scope of the session of today, but yeah, it's a bit different. So I have been working a lot over the years on power systems stability, security, and reliability. And so I want to talk about how to use machine learning, or what we have done more precisely in terms of using machine learning for taking decisions in the context of reliability management of bulk, so transmission, I would say interconnected transmission power systems. And so this is a slide with a picture that I used, I think, almost 30 years ago to explain what I was doing at that time. To explain that we get data, lots of data from the field, which is then used by power system engineers together with computations. So this is supposed to represent a control center, or a backroom of a control center, where somebody is exploiting the data that comes from the field together with significant computational power in order to generate data sets. And these data sets can be exploited by using machine learning in order to create better understanding, basically, for helping this operator or backroom engineer to take decisions in order to manage reliability, for instance. And what I want to stress as well on this figure is that when we look at these problems, we used to look essentially in terms of supervised learning problems, where we have inputs and outputs. And yes, the inputs are typically describing the state or the possible states of a power system, and these are composed. I mean, the state description is both describing the amount of generation or consumption at different points in the system, but also the topology of the system. So meaning whether some breakers are open, whether some lines are available. And I still think this was already the case 30 years ago, but I still think today it's difficult to well handle the space of possible topologies of power systems when it comes to using machine learning methods. And then these are the inputs typically, and then what you would like to predict is given injections and topology of the power system, what would be the stability level of the system, or the margin, and so on. I will give some examples later on. And typically the relationship between, even for a fixed topology, the relationship between these inputs and outputs is sometimes highly nonlinear, which means that sometimes we are kind of surprised that the system is almost collapsing because of small changes in its operating point. And so these kind of data sets can be produced by combining observations of topologies, power system states, and superimposing on these observations simulations, which will add maybe variations of the topology, will randomize a certain number of things in order to let's say to have a nice scope of study, and then run typically power flow computations or other kind of analytical methods to compute these outputs for given inputs. Okay. So this setting, or this this playground existed certainly already 30 years ago, and was already proposed actually 50 years ago as a potential field of application of AI. So in my talk, I will focus on power systems, on bulk power systems reliability management. So I have a quick introduction here just to explain what I mean by that. I think it's of interest, and then I will focus a little bit more on the work that we have done here, in particular in collaboration also with industry over the years, and for the particular topic of reliability assessment, which is one sub-problem of reliability management. And then I will, let's say, finish my presentation to give a certain number of topics where I think interesting research could be done in the future, and where good ideas are needed from the research community. Okay, so electric power systems reliability. So what we are looking at here is to make sure that the system continues to work in spite of a certain number of variations, and yes, this imposes to look at the behavior of the system, even in terms of very fast dynamics. I say here subsequent temporal resolution. I know there are some people here in the audience who know this very well. So yes, we want to make sure that the system, let's say, essentially is able to continue to function, and we are talking about an interconnected power system like the one of the US interconnections, and the threats which, when you are let's say an engineer responsible of power systems reliability, the threats that you would like to understand and let's say make sure that the system is not too vulnerable with respect to them, correspond to the, let's say, the duck curve story that was just explained very well in the previous presentation. So the variations of generation and demand, which may be fast, but also to some extent unpredictable in some cases. And they are, of course, also related to weather conditions, but weather conditions can also have other effects on the reliability of the system, like increasing the risk of lightning strikes or creating, let's say, a faster aging of equipment. And so, yes, weather and more generally environmental conditions are certainly a driving factor, but not the only one of the threats which are faced by the system. And then we have component failures, which can be weather related or state related or not. We can also have human errors and even attacks, so that we also want the system to be to some extent not too brittle when it comes to adversarial attacks. Then these are the things that I call the threats here, and then the problems that can appear are the basic overloads of lines, too much current flowing, or voltage and or frequency deviations too large to allow some essential devices to continue to operate, like generators, big generators, or even some loads that will not be able to operate if the voltage and the frequency is going too far away. And so we want these to be, let's say, controlled in a range where we feel comfortable. And then, of course, we can have, if we have overloads, we can have cascades, because there would be some protections acting, and these overloads, these cascades may also lead to instabilities and possibly blackouts. Okay, so this is a very general picture of the kind of things I want to talk about in my presentation. I just want to say there are many opportunities, like novel developments in optimization, and also there are more clever ways to do maintenance and planning of operation, and certainly over the longer term, we should also think about how to evolve the structure of the grid or of the power system more generally, in order to make it more robust and more agile to adapt to changes. So what I want to stress in this slide is that when we look at reliability management, which means taking decisions, and typically these are taken by system operators or indirectly induced by regulators. So to ensure that the reliability of the system is sufficiently high, and of course, at the same time, we want to make the impact in terms of socio-economic costs as small as possible, meaning that we want to have a, let's say, small impacts on prices, and also reduced numbers and durations and extensions of power interruptions, which also have a socioeconomic costs, of course. So there is always this trade-off that you have to pay something for ensuring that you will not later on have to suffer from, let's say, service interruptions. And so this, when you look at this general problem of reliability management, let's say from a transmission system operator point of view, you have different time scales. From long term, meaning that you talk about decisions that will take months and years to be decided, and will be having an impact over the future of behavior of the system over decades. To midterm, which is more about things that have to be done over maybe 1 year or 2 years. We are more talking about maintenance, for instance, replacement of equipment, and maybe investing in IT solutions, and let's say the general software development in terms of how we interact, how the system interacts with the users. And then the short term is really the stage where you can think that the system is relatively fixed, it's done, you know what are the resources, but you still have uncertainties, and you have opportunities to take some decisions in advance, like day ahead or weeks ahead, where you can postpone maintenance, or you can maybe make sure that you have the sufficient reserves to operate the system. And then the last stage is a real time. Of course, you can argue. I mean, I could have split this whole, let's say, horizon of decisions in more intervals. But what I call the real time is really when you can think that the system is state and is well known, but you still want to make sure that if something goes wrong, like a contingency or a line that trips or a generator that trips, you still want to make sure that the system continues to operate correctly. And so when you think of reliability management in grid development, you have to take into account, I mean, if you want to take good decisions at that stage, you have to take into account the fact that they will have an impact on the future operation of the system in terms of asset management, so in the midterm and in the shorter term. And when you do operation planning, of course, very obviously, if you are day ahead operator who takes decisions for the next day, essentially what you're trying to do is to take these decisions which will make the secure operation for the next day to be feasible in spite of all kinds of uncertainties, and while taking into account how real-time operation works. So I mean, the whole slide here is really the story of research on which we are working here. And so when you look at these different, from short-term to very long-term reliability management problems, they are typically divided into two parts. One is the reliability assessment. So you assume that you know the main decisions and you want to just to see what would be the expected level of reliability of the system over a certain horizon. Let's say you are day ahead and the market clearing gives you information about what would be the amount of generation of different big plants, and you have forecasts for load and renewable generation. Then the question of reliability assessment is to find out what would be the expected level of reliability over the next 24 hours. So this is typically what I call a simulation problem. It's a large-scale stochastic simulation because you have uncertainties, and because, of course, the system is large-scale and it's non-linear, so it's not, I mean, you can do parts of it by doing some analytical, let's say, approximations, but overall you need to probably to pay the price for simulations here. And then, let's say in the same context, if the outcome of this reliability assessment that you do day ahead, given the market outcome, tells you that, well, it's not accepted. What you think is that the situation is not going to be manageable for the next day, then you need to find out some decisions that you can take now, the day ahead, in order to make sure that the reliability level is within the bounds, let's say, which are prescribed for that. So that's typically then an optimization problem, stochastic, because you have uncertainties, and again, a large-scale optimization problem. And of course, I want to stress here that we are talking about covering ourselves with respect to contingencies and situations which do not necessarily have been experienced many times in the past. So beyond data that could have been collected over the past periods of time, we need physical models. And these physical models, of course, have limitations, but they will help us to try to understand how the system would respond in situations where we have not yet observed the operation of the system. So this is, I think, this combination of physical models and uncertainty models coming from the data are very important. Okay, so So let me give some examples of applications that we have done. So I will start with real time and then with shorter time look ahead mode, like a few hours or days ahead, and give some comments on how to extend this over a longer term horizon. So let's say real-time mode reliability assessment would be to do every 5 minutes based on the data that you gather about the real-time simulation, XRT, the risk induced by contingencies that could occur over the next time horizon, let's say 1 hour. We have a set of contingencies. So these are the kind of events that you would like to study and see whether in real time they are creating any risk. So that's a set of contingencies. It's a function of real-time conditions because it depends possibly on whether some lines are under maintenance, whether there are some works somewhere, or even on the weather conditions. And then you have, for each one of these elements of this set of contingencies, you have a probability. It's a simplified reasoning here, but this is a probability that that contingency could occur, let's say, during the next 1 hour period. It depends, of course, on the particular contingency, the particular line or generator that could trip, or the particular short circuit or other kind of contingencies that you want to study. And it depends also on the data that you have about the situation in which the system is currently, the real-time state. And then we have a function which measures, based on the state of the system and the particular contingency, the severity. So this could, for instance, be, if I'm in a particular state, what could be the amount of load that would have to be shed in order to minimize the impact of that contingency. So it can be 0 if the contingency is benign, or it could be, let's say, a few hundreds or thousands of megawatts, and of course taking into account also the duration of that service interruption. So this is an example of such a function measuring the impact, the severity of a contingency. So with this, what we want to do in real time is essentially estimate the expected value of this severity, which is the sum of all the contingencies, where the probabilities weight the severity. Yeah. And this can be already a complicated thing to do because the number of contingencies can be possible contingencies can be quite large, and the computation of these severity functions may be computationally very intensive. And another version of that problem is to say, what is the probability of overly large let's say service interruptions or overly large contingency severity. So this would be estimating the probability that this severity is larger than a certain threshold that would be given in advance, given the state of the system as it is here. Okay. And yes, in practice, what operators, TSOs, and system operators can do to estimate the severity is to compute them via power flow computations, optimal power flow computations, or more complex time domain simulations. So for this scenario, what could be done with using machine learning? So this function, the severity function, is generally expensive in CPU time. Still, this function will be evaluated as often as possible by the TSO using his EMS software. So yielding a data set where you have basically pairs of descriptions of real-time conditions and contingencies, and the value computed by some software of the severity of that that would have been the severity of that contingency in that particular state. And so we can obviously use machine learning, which is supervised machine learning is a framework to use a data set of inputs and outputs. And so the inputs would be these pairs here, and the outputs would correspond to these values. And so that we learn a function that predicts these values well based on past data. Okay, and that's really something that has been proposed many years ago. And of course, we can use regression or classification techniques depending on whether we want to estimate in the end the value of this, or only know whether the value of this severity is bigger than the famous threshold that I mentioned earlier. Of course, the idea is that once you have learned, once you have applied machine learning on past data, you can use the model here produced by machine learning to do evaluations of that function in a much faster way. So it would allow you to maybe to screen more different contingencies at every time step, or reduce the number of the delay between successive time steps where you do the contingency analysis. And of course, the second important assumption is that there are good methods able to learn this in an efficient way. Okay, so here's a very old study. It dates back to the 1990s. It was a study that was carried out in collaboration with the French utility. At that time it was called EDF. And we were focusing on voltage, the risk of voltage instabilities, and the region that you see here. This is the so-called Brittany part of the French system, which is weak basically in terms of reactive power support. Was weak at that time and is still weak today, actually. So basically, this study region is covering a load which is about, let's say, 10% of the whole French system. We have covered in this study topologies from the full complete topology to various systematic n-1 and n-2 topologies where lines are out of operation, and combinations of lines and generators and other lines. And we used a relatively detailed model to study the behavior of that system, which is described here. So for a given operating point of this power system, what we computed is the so-called pre-disturbance load power margin. This is how much you can increase the amount of load in the system without having any problem, while supposing that all generators are still in operation and continue to serve, and the lines are there and continue to serve the load. So, of course, if you are in a stage where the load power margin is very large, it means that if the only thing that you care about is the variation of load, you're kind of safe in terms of reliability. And then for each contingency, a contingency could be, for instance, the loss of a line here. What we computed is also the load power margin in combination with that contingency. So meaning that if you lose a line, then you can continue possibly to operate correctly for a certain level of load, but it might be smaller than the one. And so these are the classical nose curves or PV curves that are used in voltage stability studies. And so you have the so-called post-contingency load power margin, which is taking into account the particular contingency, and the pre-contingency load power margin. And the difference between the two is the severity of a particular contingency in a particular state. And so in order to study this, what we did is we developed software in order to do Monte Carlo simulations, where we sample different operating conditions, different disturbances or contingencies, but also different assumptions about the model, the dynamic and static model of the system. So for instance, what is the sensitivity of the load to voltage changes, or these kind of things, which are parameters that you typically do not know exactly. And so by random sampling, you can generate combinations of these. Each one of these gives you a simulation scenario, and this simulation scenario can then be simulated in order to see the resulting behavior of the system. And what we did was using at that time for these situations, quite large cluster of computers in order to generate this database of simulation results sufficiently quickly. And so the results are stored in the database, and you can then exploit these kind of results in order to build or to understand the relationship between variables which characterize the state of the system and the severity of a contingency, for instance. And so this particular graphic here shows the severity of a particular contingency, which is a loss of a certain line circuit, actually one of these two lines. And in terms of how much it reduces the load power margin. So on average, over the whole set of operating points and assumptions about the physical behavior of the system, so the model hypothesis, this is a 100 megawatt severity. But there is a standard deviation of about 100 megawatt as well. So in some cases, it's much bigger than 100 megawatt. In other cases, it's smaller. And so the regression tree machine learning approach tries to find out which characteristics, which features of the operating state of the system explain this variance of 111 megawatt. And so the first parameter that was found was to say that, well, we have to look first at whether the second circuit, so the parallel line here, is or not in operation. Obviously, if you lose this line while the other one is already out of operation, this has a different impact somehow on the security of the system than if you lose a line while the other is still in operation. And so what we see is that if the second circuit is in operation, in our data set computed by Monte Carlo simulation, the average severity is smaller, and also the standard deviation around this average is much smaller than this 111, whereas on the other side, we see that we have a smaller set compared to the total sample, which was here of 2,610 plus 165. But in this subsample, the average severity is much bigger, really much bigger. And also the variance is, the standard deviation is higher. And then after that, first feature which was identified by the machine learning algorithm. The second one is looking at the reactive reserve. Actually, this is a reactive reserve of a subset of generators located in this area. I don't want to go too much in the details here, but again, if the reactive reserve is bigger or smaller, then the impact can be bigger or smaller, and so on. So this gives actually a relatively simple analysis of the relationship between the features describing the operating point and the severity of a particular contingency, which allows you to reduce this, let's say, uncertainty that you have about this severity from 111 to something like 22 megawatt. And this was estimated to be in the same order of magnitude as the background noise here in this problem, related to the fact that we don't know the exact parameters of the model that we use to simulate the behavior of the system, so that actually this very simple model is looks like being sufficiently precise, almost as precise as a fully detailed simulation would be done. And it's allowing you to compute the severity of a contingency in terms of reduction of the load power margin. So you could combine several models like this to figure out or to estimate the severity of a combination of contingencies. Actually, that was the, let's say, the level of thinking that we had reached in the 90s on this problem. And also, we had developed a kind of nice framework in order to combine a toolbox of automatic learning algorithm. At that time, it was quite clear that machine learning would be a field leading to novel developments. So there would be new algorithms that would be useful in order to analyze such data sets, and also in terms of the other side of computational techniques which allow us to compute contingency severities or stability degrees, or all kind of parameters of interest when you do reliability management of power systems. Okay, so I think I have to speed up. And so the more recent work that we did is that we are able to build such models using machine learning. And if we look at the problem of taking decisions rather than in real time, we want to assess the security level of the power system a day ahead, or a few days ahead, or a few hours ahead in time. Well, in that case, we have to take into account the way the operator is going to react in real time. So what we are going to simulate is not only the physical behavior of the system, but it's really the combination of the potential physical behavior of the system with respect to contingencies, which are the things that the operator in real time would look at, and how he would react in case it turns out that at a certain moment of time in the day, some contingencies are dangerous. So what we do there, instead of simulating just the physical behavior of the system, we actually simulate the way this operator will react. And for that, we said, okay, we could use something like a security constrained optimal power flow. And so we could apply machine learning in order to predict what would be the result of applying a security constrained optimal power flow over trajectories that could be happening over the next day. So I'll show this here. So you have a forecast, and then you, in day ahead operation planning, maybe there are some decisions that you want to submit to the reliability assessment study. And you will do some Monte Carlo simulations of what could happen over the next day using day-ahead uncertainty models, meaning that you are uncertain about what will be the exact amount of renewable generation in different parts of the system. And there could be some outages and things like that. And so you want to see how you think the life is likely to be go during the next day. So you simulate when you are in the day-ahead decision-making context trajectories of how the system would operate over the next day. So this is a simulation of real-time operation. And for this real-time operation, we apply a certain number of successive n-1 constraint. In this case, in this study, DC with DC simplification, security constraint OPFs. So if you have 24 hours and 1 hour time step, we will, for each trajectory for the next day, have a sequence of 24 security constraint OPFs that will be computed. Out of that computation, we will have costs of decisions that would have to be taken by the operator. And for each, given the decisions that would be taken according to that optimization strategy, at each stage, we would also be able to assess the reliability of the system by computing the expected severity of a set of contingencies beyond possibly the n-1 contingencies that are explicitly covered by the operator. And so we can then apply machine learning to this kind of data set. And so what I show here is different cost terms. So the total cost of operation incorporates the cost of redispatching classical generators, cost of load shedding, and the cost of wind curtailment. And beyond that, an expected cost of service interruptions, of contingencies that are not really covered by the DC scope model of the operator. And for each one of these computations of these quantities, we have applied different machine learning algorithms, supervised learning algorithms, to find out which are the most accurate ones and how accurate they were. And so what we see here is that, for instance, for the total cost, the neural network, deep neural network is almost providing 96% of the explainable variance. So it's a very accurate one. Whereas if you look at other specific terms, it may be some other method, some other supervised machine learning method, which is the most accurate one. So this is just to convey the idea that there is not a single good machine learning method. It's really of interest to have a toolbox of techniques, and in some cases, it's one that works better than another. Beyond this, let's say, accuracy evaluation, we also see that we can use some of the methods to understand which of the parameters describing the next day scenarios are the most important to explain the variation of security level. Again, a bit similar to the regression tree. Here it's a diagram measuring the so-called feature importance and telling us that on the studied system, while the most important variable, the one that really provides almost 20% of the explainable variance, is the status or the level of generation of this particular generator. And the second one is the status of this particular line, whether it's in operation or not for the next day. So I think it's of interest to show these kind of things, to show that with machine learning you can also try to understand what's going on in your problem.
So Luis, I'm not sure you are monitoring the chat, but we are against the time here, so you
yes,
know you will need to wrap it up.
Realize this.
Yeah.
I fully realize this. So I think I go to the conclusion.
Okay, thanks.
And leave opportunities for the let's say the panel session later on to discuss a little bit. So I had another part in my talk about combining machine learning, supervised machine learning with variance reduction techniques. So when you are day ahead, you can learn a model about the relationship between what would be the next day realization. But this model, of course, will depend on the data set that you have used to learn it. So it may be biased. So if you now plug this model into a Monte Carlo simulation, according to the uncertain distribution that you have for the next day, the estimate may be biased. But you can actually combine such a model with evaluations of the function that you want to, of which you want to estimate, let's say, the expectation, and rather than estimating the expected value of the severity, you estimate the expected value of the difference of the severity of what your proxy model built by machine learning predicts, and what is the actual outcome of your detailed simulation model. And if the proxy is not too bad, then you can actually use this in a kind of win-win situation where you reduce the number of simulations needed to obtain the same accuracy. And this is what was studied in the second part of my presentation. Beyond that, I wanted to give, let's say, three directions of research in this overall field of trying to use machine learning for reliability management of large-scale power systems. I think there are many opportunities to find out how to use machine learning to incorporate active distribution systems reliability into these studies. For the time being, we don't have very good models of how the distribution systems react to whatever is going on in the let's say the transmission system. And so we need to find out ways to exchange information between DSOs and TSOs. And also, I have done mostly work on the, let's say, the classical setting of security or reliability analysis, where we think of contingencies as being, let's say, generated without trying to specifically attack the power system, so they are not adverse to the power system, and also they are essentially focusing on the physical part of the system, whereas I think that more and more we have systems where the cyber layers become very important, and these cyber layers are let's say creating novel threats, part of them being related to adversarial attacks. So I think it's very important to try to work on that, and this is, I think, changing the way you can try to apply machine learning. And then, of course, I have been talking about assessment on purpose, because difficult to talk about everything at the same time, but you also have optimization and control. So how to learn exactly the good decisions to take. This is ongoing work as well. So thank you, and sorry for the let's say the too much time that I took here.
Thank you very much, Luis.